Hi everyone, and today we are presenting the first part of mini-series of Introduction to the Concurrent Programming from our veteran speaker of HIDR and our Jagger conferences, and my best friend Nikita Koval, who is now a researcher and
Hi everybody, and I'm glad to give a talk, to give a mini series at Hydra this year, and thank you, Dmitry, for introducing me.
And Nikita, how do you think? What's the expected auditory of your mini-series? Who is it intended to?
So I would say that Hydra focuses on two global topics, on concurrent programming and on distributed programming. So usually there are two people. So people who work on concurrent systems and who work on distributed systems. And in my opinion, it would be great for the guys who have background in distributed programming to have an introductory talks about concurrency stuff, and I really wanted to fill the gap, and that's why I'm presenting this mini series this year.
Okay. So you think it's more for practitioners or for people who are interested in theoretical basis of the matter?
I would say for both. We'll start with the classic, mostly theoretical algorithms, but tomorrow, for example, we'll talk about modern queue algorithms, which are very, very fast and scalable, and it's likely that somebody will use this algorithm or its modification in practice. So these talks are for both people who are interested in theory and for people who are interested in improving their practical skills.
Okay, so I think we could start now.
Sure, let's start. And as we already mentioned, I will give several talks, actually 3 talks. The first one will focus on the classic stack and queue algorithms, and we'll also discuss the standard definitions, such as correctness definition or progress guarantee properties, which every programmer who works on concurrent systems should know. After that, tomorrow we'll have 2 talks, one on fast queue algorithms and on the flat combining technique. I will talk about it tomorrow. And the last talk is about data structures with relaxed behavior, so which are kind of incorrect in general, but still interesting and important, useful in practice. So today, focus on the classic stacked queue algorithms. And before talking about the algorithms themselves, let me give a small introduction into how you should write concurrent code in almost any situation. Usually, you use Mutexes. So mutex is the most fundamental construction in concurrent programming, which allows at most one thread to be in the critical section to hold the log. And the pattern is the following. You acquire the log, you do the job, and release the log. And it's guaranteed that in this critical section, at most one thread can hold the log. So this critical section is executed sequentially, and the log synchronizes concurrent threads. Let's try to build something on a mutex. For example, let's build a counter. simple structure. So we have a log and we have a counter value. And in order to implement any counter operation, for example, get and increment operation, we acquire the log, we perform the increment, and finally we release the log. And how does it work when there are two threads? So, for example, we have a yellow thread, so it acquires the log, it increments the value, and if another thread comes, so you see that this increment is not thread safe. So if two threads would perform this increment concurrently, we'll have a yellow. But now, if another thread comes, it can't proceed because the yellow one holds the log. So the purple thread, it should wait until the log is released. So it waits, and after that, the yellow thread releases the log, and only after that, the purple thread can acquire the log and proceed. Okay, and this scheme can be used for to build any sequential data structure concurrent. So what we need to do when we have a sequential data structure is to guard all functions with the log and unlock invocations. So if, for example, we have a counter, we have get function, increment, get and set, and so on. So we should guard all of them with this lock and unlock. And in this case, the data structure will be correct. And this pattern is called the coarse-grained locking. And that's how you should write concurrent code in almost all situations. Because if this solution works, that's great, because it's simple to implement it and simple to maintain. It's easy to maintain it. And so if the performance is good enough with this solution, so wow, great. You don't need to deal with all these backbone concurrent algorithms. But here's the problem. If we use logs, there is no progress guarantee, because in fact, all the functions are applied sequentially, because we cut the invocations by the log, and thus the algorithm never scales. And sometimes we want algorithms to make progress concurrently. We want them to scale. And to build when we're talking about scalable algorithms, when we're talking about progress, we usually mean log freedom. Log freedom is the classic progress guarantee, which guarantees that the system in general makes some progress. So I mean that independently on what all the threads do, we have some progress, so the operation never stuck, and we don't achieve log freedom with the mutexes, because if the thread that holds the mutex is stuck, then all other threads are stuck as well. So there is no progress, right? And with the log-free algorithms, if some thread doesn't do anything, then other threads still make progress. We'll see it. We'll see it in a couple of minutes. Okay. But here, what's important that when we talk about non-blocking algorithms, about almost all concurrent algorithms, the main building block for them is the compare and set operation. And this is a special operation. It's available in almost all processors. And what it does is it tries to atomically change the value located by the specific address from the expected one to the new one. And if the value is still the same as expected, then the class returns true. Otherwise, if it fails, so there is no update, it returns false. And this is the main building block. And let's try to improve our count implementation with the compare set. For this, we have an infinite loop. So we don't use mutex anymore. We have an infinite while true loop. And in the beginning, we read the current state of the counter, and we try to update this state. So we try to increment it, and if the counter value hasn't been changed, then we succeed and return the result. Otherwise, we start from the beginning. So if we fail, it means that another thread has already updated the counter value, and we must obtain this new value and try to apply the get and decrement operation again. And importantly, if this case fails, it means that another thread has just made progress. And that's how lock freedom works. That's how we guarantee the system-wide progress. When we try to update the state, we either update it and this thread makes progress, or we fail, and it means that another thread has made progress. And similar to the mutex, we can.
Nikita,
yep.
Nikita, could you switch here? I suppose with some mistake or error, get an increment should return old value or new value?
Nice catch, actually. Get and increment should return old value, of course. So instead of return current plus 1, it should be return current.
Okay. So just.
Nice catch. Thank you.
Okay.
But the rest is the same, right? So we update the count state, and we return the result if we succeed. Otherwise, we start from the beginning. So this way, we can make any sequential algorithm concurrent and lock-free using an universal construction. So with the mutex, we had coarse-grained pattern. So we had a mutex, and each function call is guarded by lock and unlock invocations. With compare set, we do a similar thing that we just did with the counter. We have an infinite loop. We read the current state of the data structure. We make a deep copy of it, apply the function to this copy, and try to replace the pointer to the previous state of the data structure to the new one. So we try to replace the references. So we try to atomically apply this function. And if this case succeeds, then great, this function has just applied, we can return the result. And if not, it means that another thread has just updated to the data structure, and we start from the beginning. And importantly, in the universal construction, we always make a new copy of the whole data structure. Thus, we guarantee that each reference corresponds to so we guarantee that references correspond to different data structure states. Okay. So that's how the universal construction works. Of course, as we need to make a deep copy, this universal construction is mostly theoretical, but I would like just to give an intuition how to make any algorithm correct in the concurrent world and lock free at the same time. And here probably it's good place to stop for a while and to ask questions. And I would also like to remind that we have a say small lag in half a minute between the live and the video you see. So please ask all the questions during the presentations. So when we stop, Dmitry can.
Okay, we don't have questions in the chat, but I would like to pinpoint some moment. But you are making a copy, and do you have here for secretion data structure a pointer of the structure itself in this construction? Because if it's not a single word structure, it would be not atomic copying. So how would you implement the case?
You're right. So this equation of data structure field is just a pointer to the data structure, and each time we update it, it's a new pointer. That's why we can guarantee that if the data structure is dated, it's a new version.
Okay, so here sequential data structure should be a pointer.
Exactly.
Okay. Okay, and yes, and we have a question: shouldn't be last parameter of the class the result, not the copy?
No, the result is the result of the function. For example, if this sequential data structure is a priority queue and we add a new element to this priority queue, the result is unit. It's what? It's nothing. So we don't have any result, but we update the priority queue. And the idea that in order to add a new element to the priority queue.
So you mean that the function should modify copy in place?
Yeah. Yes. So we make a copy. We modify this copy, and we store the reference to this copy by the highlighted component set instruction.
Okay. And we have a question about how our deeds interfere with Java memory model, but I think maybe it should be discussed later in more thorough discussion.
As for memory models, I would suggest moving the discussion to the discussion zone after the talk. Okay?
Okay. So let's move forward.
Okay. So as we already discussed, this construction provides block freedom progress guarantee, because if the class fails, it means that another thread has just made progress, so we guarantee the system-wide progress. And now we will move to more complex algorithm, to a stack algorithm. And first of all, we discuss the structure of the stack we are building. The idea is that we represent a stack as a linked list in the nodes of which we store the elements. And we have one reference to the top node in the stack. So here is a stack to which we first inserted 1, then 2, then 3, then 4. And that top reference references the node that stores 4. And by the next pointers, this node references 3, then 2, then 1. Okay, and the last next pointer, it doesn't reference anything, so it's actually null. And in order not to draw this, if there is no error, it means that the field is null. So the structure is the following. So we have nodes. Nodes store the next node and the value, and the stack stores the reference to the top node, or it also can be null if the stack is empty. So to insert a new element, we create a new node and update the top reference, like on this diagram. So let's try to do this, and let's try to do this in concurrent environment. How could we do this? We can do this the same way as we did for the counter and as we did in the universal construction. We did the current state. So you see, the state of our stack is just the top reference. So we read this state. We create a new node that references the current top node in the next field, and that stores the inserting element. And we try to update the top field with the initially obtained top, or from the initially obtained top to the new one, to the new node. So we read the top, we create a new node, and we try to update the top like this, right? That's how it works. And in order to remove the top element, we simply move the top forward. So the code is pretty similar. We similarly first read the top field. Then we read the next pointer of this top field and try to update the top field from the initially obtained current top to the current top next. So we try to change the reference of top atomically, because we do this by comparing set instruction. And if this cast succeeds, it means that we've successfully removed the top node, so we can return its element as the result. So maybe questions here, Dmitry?
No, we don't have any questions from our auditors so far.
Okay, maybe we'll stop in a couple of minutes then. So, importantly, if from pop and we remove the last element, then top next can be null, and we update from the we update the top reference to null, and it's okay because it's the last element. Then after we remove it, top should be null, as we initially discussed, because the stack becomes empty. Also, it can be possible that the stack is already empty, and we have to check for this corner case as well. So when we did the current top value, we must check that it is not null. And if it's null, we can, I don't know, we can return null, or we can throw empty stack exception, like in this pseudocode. But we should deal with this corner case somehow. Okay. And here's the question.
Maybe I would also mention about we have we need some warranties about visibility through the top. It's probably volatile in the case of Java memory model or something like this, because we are operating with it before cache, so we should correctly see references elements.
Yeah, that's correct. But here we assume that all that everything is volatile, just for simplicity. So
Okay,
we don't want to think about memory models in the introductory talk, right?
Well, I am pointing it because in auditory already asked about some moments in this perspective.
Thank you. So here's the question. So we have a stack, right? And are these push and pop operations lock-free? Take 5-10 seconds to think about that. Okay. Actually, it's lock-free because each time the cache fails, either in push or in pop operation, it means that another thread has just applied its operation and made progress. So if the cache doesn't fail, the operation finishes, that's great, no problem. And if the cache fails, another operation has just finished and still no problem. So it's lock-free. But when we talk about lock freedom, it's possible that one particular operation cannot make progress because other threads, for example, like here, other threads update the top reference, and we are very unlucky, so we try to apply our operation and we fail again and again, and it's an infinite process. It's theoretically possible, but in practice, it almost never occurs. So when we talk about lock-free algorithms, that's usually what you need. Okay. And what about correctness? So with the counter, it was obvious that its implementation was correct, right? And here we have a more complex algorithm, and it's not trivial to say whether it's correct or not. And more importantly, what is correctness? How to decide whether this implementation is correct in the concurrent scenario and another implementation is not? We need a formalism for that. And before talking about formal definitions, let me give you some insight on which executions we want to allow and which we don't want to allow. For example, here, the stack. We have a stack, we have two threads, two parallel threads. In the first thread, we push A and we pop. And in the second thread, we push B and we pop. And the pop in the first thread, it returns A, and the pop in the second thread, it returns B. So this is the execution we have. Here's the question, is this execution correct? So actually, it's correct, because we can think that the first thread started, applied to push, applied pop, then the execution moves to the second thread, and the second thread applies push and then invokes pop. So we can we have an intuition on how this result could be obtained. So it seems correct. Okay, what about this one? What about this execution? Now the pop in the first thread, it returns B, and the pop in the second thread returns A. Is this correct? Yeah, it's still correct, because we can think that the push A was invoked in the first thread, then the execution moved to the second thread, and push B was invoked, then the execution moved back to the first thread, so pop was invoked, returned B, and after that, in the second thread, pop returned A. Looks correct, right? And this, so these are pop operations, and they both returned A. Is that okay? Our intuition says, no, it's not okay, because we inserted A at once, and we've retrieved A 2 times. We haven't inserted A 2 times, so we don't want to allow such executions, right? So, no, it's not okay. And this one, so here we have some synchronization between threads, and this happens before relation says that the push operation in the first thread has been completed before the push B in the second thread has started. So we guarantee this synchronization somehow. We know it. And can we obtain this result? Can we obtain? Can the pop in the second thread return A? But it can't, right? It can't, because we know that push A happened before push B. So the top of the stack is at least B. Or it's also possible that the push C in the first thread has already been applied as well. So the top is either B or C, and definitely not A. So it's possible for this pop, if the stack is correct, to return A. You don't want this execution to allow. So we ban this execution as well. And we need to, so we have some intuition on which executions are good, which are bad, and we need to formalize the correctness property. And many years ago, more than 30 years ago, actually, Herlihy and Wing proposed a correctness condition for concurrent data structures, which is called linearizability. Linearizability is the standard correctness condition for concurrent algorithms. And in short, we call the execution linearizable if we can express it with the sequential execution. So remember, we tried to express our concurrent execution with the sequential one. So it's linearizable. It can be expressed with the sequential execution that doesn't violate the original happens before order, which is the program order and the synchronization order. And this execution must show the same results as the original one. And we call the data structure linearizable if it's guaranteed that all possible executions are linearizable. And for example, here in our stack, the places of the linearization, the points of the linearization, the points when the synchronization happens, when the operations become visible for other threads is the successful compensator invocations that update the top reference for the stack. And that's why this stack is correct, because once the cast is applied, then new top node is successfully installed, and the state of the stack has successfully been updated. So it's a good place to stop for a while, maybe discuss something with Dmitry and with the audience.
Well, we still don't have questions. Maybe everything is crystal clear, but maybe some auditory just need some time to comprehend the issues discussed. I think I have some points about linearization, but they will be too complex for the quick answer.
It's important that this linearizability definition is kind of simplified. I want to provide the intuition first, because the original definition we need to. It will take.
It will be too formal and
it will take a while. Right, it will take a while to understand it. But the idea is still the same.
Okay. Well, we still don't have any questions. Maybe people just need to bunch some comprehensions. So no questions for a moment.
Okay, let's then move forward. Okay. Let's extend this stack implementation with the top function that simply reads the top element. How would we do this? We can just read the current top node, and if it's null, then the stack is empty. Remember, in this case, let's return null. And if it's not null, then we simply read the element field in this node and return it. Very easy. And the synchronization, the linearizability point is reading the point when we read the top reference. Okay. Okay, I have a question here. Is this top implementation log-free? We don't have even an infinite loop. We don't have any update here. So it's guaranteed that this top finishes in a bounded number of steps independently on what other threads do, right? Because we just read the data. And yes, indeed, it's log-free. What is more, it is wait-free. So wait-free is a stronger progress guarantee, the strongest one. Now, for example, log freedom guarantees that there exists an operation that finishes in a bounded number of steps, thus guaranteeing the system-wide progress. And as for wait freedom, it guarantees that each operation finishes in a bounded number of steps independently on what other threads do. So wait freedom is a stronger guarantee than log freedom. And usually read operations, such as reading the top element in our stack, can be wait-free. That's the pattern. So, Dmitry, if you have a question.
No, not for the moment. And we didn't get any.
Okay.
Oh. Our auditor is shy for a moment.
Yeah. So if there is no question, we can move to the state-of-the-art Michael Scott queue algorithm. So this is the paper in which Michael and Scott originally introduced the algorithm. It was almost 30 years ago. Wow. So,
well, actually, we see only POC 96, but no paper name. Maybe you should. Oh, now we see it.
Interesting. Yeah, I have to see it. And this Michael Scott queue is the standard queue in many languages. For example, if you're familiar with Java, you may be familiar with the concurrent linked queue standard collection. And under the hood is the queue we are going to talk about. It's the Michael Scott queue. And the structure is similar to the stack. So the structure of the queue is also a linked list, but with two key differences. First of all, as it's a queue, not a stack, right? We need to maintain 2 pointers. We need to maintain the head pointer and the tail pointer. So, but the tail pointer we understand where to insert an element, and by the head pointer we know where to retrieve the first element. And the second difference is that the first node in this queue is a dummy node. It doesn't store the element, and the first element is stored in the next node after the one pointed by head. It simplifies the design because in this case we can represent an empty queue as a queue where head and tail pointers reference the same node, the same dummy node. So this node logically doesn't store an element, just a dummy node to simplify the empty queue representation. So here's the structure. We have a node, and each node stores the next pointer and the value, and the queue itself, it has two pointers, head and tail, and initially they reference the same node. And to insert a new element, we create a new node with this element. We update the next pointer of the current tail. Thus, we add the created node to the linked list. So physically, it's now in the linked list, right? And after that, we update the tail pointer. Okay. And the main problem here that if you want to make this change correct in the concurrent environment, we need to perform this next point update and the tail update atomically. So let's try to do this. First of all, as we need to. First of all, let's see how sequential implementation could look. So here we create a new node. We read the current tail. We install the new node into the next point of the current tail, and we update the tail. And let's try to make it concurrent. Let's try to insert component set in a proper place. And as we first add a new node to the linked list physically, we can do it by cast. This way, if this cast succeeds, then it's guaranteed that that's we who successfully inserted a new element, and other threads can't insert an element, because in this case we try to replace null with the pointer to the newly created node. And only one thread can succeed with this case, because after this case succeeds, the next pointer is no longer null. So they did that. We do the next pointer update by component set, and after that we update the tail point. And if the cast fails, we restart from the beginning. So we delete the tail pointer and we try to perform cast. We delete the tail pointer again if the cast fails again, and so on. Let's try to see how this algorithm works. So we have two threads and two anchors. And for example, the yellow thread starts, it wants to insert 3. It creates a new node, then it reads the current tail and updates the next pointer of this tail. And after that, the purple thread comes. It also creates a new node, but it can't update the next pointer of the current tail because it's not null. And importantly, it can't make progress, because now it should wait until the yellow thread updates the tail point. Before that, the purple thread, it starts from the beginning again and again and again, so it's kind of stuck. And you see, this algorithm is blocking. We don't use logs here, but the algorithm is blocking. There is no log freedom guarantee. And we need to fix this somehow. And to fix this, I suggest the purple thread to help the yellow one to move the tail. Right? Because that's the problem. The purple thread can't make progress because the tail is out of the date. And if it's possible to help in updating the tail, then the problem is solved. So let's do this. Then, in order to update the tail pointer, we introduce cast operation again. So, if the purple thread would become in such an unlikely situation, then now it can update the tail pointer by trying to replace the current reference with the tail with the reference to the next node. And if this component set succeeds, then the helping procedure was successful. And if it fails, then the tail has already been updated, so no problem again. And importantly, the initial operation that successfully inserted a new node, it also has to update the tail pointer by a cast operation, because if it updates it by just by plain write, then the tail pointer can become outdated, because if for example the yellow thread is stuck for a while at the point before the tail update, then it's possible that a lot of function has just been invoked and the tail is somewhere forward. And if we update the tail by a plain right, then we move the tail pointer back. It's not okay. We don't want to do this. That's why we do it by cast. So let's see how it works. So in this situation, when the yellow thread has successfully inserted its node into the linked list, it hasn't been updated the tail pointer yet. In this situation, the purple thread can help the yellow one to update the tail point. And after that, if the tail pointer comes, it doesn't update, or if the yellow thread comes, it doesn't update the tail pointer because it has already been updated. So it finishes, and the purple thread can apply its operation because now the structure of the queue is fixed. So maybe questions here.
Well, our Telegram channel is quiet, so auditory doesn't have questions for the moment. I would ask a speculation. Can we help moving tail using the loop? So we will pass using next, why don't encounter null, and trying to cast on the last observed element?
Yeah, I think that's a good idea. We can have an optimization that if the tail is has to be updated, then you mean that we still insert the element and let me think. So am I right, Mitty, that the optimization you suggested that in this case, the purple one can still find the actual tail, and after that update the tail point. So
yes, we could traverse using tail as fast as we can and as far as we can, and then.
Yeah, that's a good idea. We certainly can do that. What is more, that's how the implementation in this standard Java library works, as far as I remember.
Okay.
Yeah. But the classical algorithm doesn't have this optimization.
Well, that's usual optimization because plain volatile reads are much faster than cast operations because of the nature of it in the hardware.
That's true, but if we talk about optimizations, then you can come to my second talk on modern queues, and I will present a much more efficient queue algorithm, and it's a much better optimization than...
No spoilers.
Okay, no spoilers.
Yes,
so,
okay.
We're kind of lack of time, so let's continue.
Still no questions? Okay, so let's move.
Okay. The question about process guarantee, as usual, is this thank you lock-free? Yeah, now it's lock-free. It's obvious because if we can't add a new node to the linked list, then we help the concurrent thank you operation to move the tail forward. And if after that we can't add a new node to the linked list again, then it means that one more operation has just linearized, and thus we guarantee system-wide progress. So if we start the infinite, we start the operation from the beginning again and again, we still guarantee the system-wide progress here. Okay, let's implement the deque operation. And the deque operation, technically, it's the same as the pop operation in the stack. So we simply move the head pointer forward. And after that, in this case, after we move the head pointer forward, we return the first element, we return 1. And this node with 1, it becomes the new dummy node. So how does this work? We read the current head pointer. We obtain its the next node. We check whether the queue is empty or not. If it's empty, then we throw an exception, like in the stack, or we return null. And after that, we try to update the head pointer from the initially obtained head to its next. And if this call succeeds, then congratulations, the deque operation is done. And we return the result. And if this call fails, then we restart from the beginning the same way as we did in stack. Okay. Here maybe you have a question or no questions again. And I also see that the slides, okay, you see to sum up slide and wow, I see another one. Yeah, to this one. So, any question?
No, we still don't have questions from our auditory.
Okay. Okay, so this is it. So in this less than 1 hour talk, we learned how to make sequential data structures correct using mutexes. We know the coarse-grained locking technique. We also learned a lot of stuff such as compensated operation, universal lock-free construction that leverages compensates. We learned what the standard correctness property, the linearizability is, as well as the most important lock and wait freedom progress guarantees. And of course, now you know how to implement stack, Schreiber stack, and Michael-Scott queue algorithms. And if you want to sharpen your skills in concurrent programming, I've also prepared several assignments for this series, and it includes the stack and the queue algorithms. In these assignments, you have some code prepared, so you don't need to write to implement the stack and the queue from scratch. You just modify the existing sequential code to make it concurrent. So feel free to check this GitHub repository for the segments. And thank you for your attention, and don't know whether we have time to discuss something.
Okay, I would suggest to leave URL visible for auditory.
So we are
just move one slide before, so auditory had more time.
Sure.
Okay.